Modeling and simulation is very important in chemical engineering. So modeling is nothing but that is mathematical modeling. Mathematical modeling is nothing but it is abstract representation of any physical process by means of equations. So in order to write these equations you should understand what is conservation of mass, energy and momentum. And after you write these model equations, they have to be solved by means of any using mathematical technique. Like you can use direct C language code, or you can use any available software like MATLAB or any other software you can use. So and this process modeling will have, so initially we will understand now what are the uses of mathematical models and what are the principles of mathematical models and how do you write a mathematical model equation. So now we will discuss in this class. So modeling is it's an abstract representation of any physical process by means of equations. And simulation is nothing but solution of these model equations by using any mathematical tool or software. And why this mathematical modeling is required? So that is in order to understand the complexity of any process, so you have to write the equations and then you can understand what is the, so what is the process involved in that. So you can understand by means of writing the equations very easily. So that is instead of doing experimentation. So because experimentation involves so the money and all, so instead of doing experimentation, so you can do so mathematical analysis by knowing the conservation of mass and energy and momentum, and then you can write the equations and solve them by means of any mathematical tool. So this mathematical modeling it complements so the process, but it does not replace the theory and experimentation. So experiment also very important, but before you conduct the experimentation, the mathematical modeling helps in understanding the process whatever you are going to run the experiment. So mathematical modeling is very important and it has many uses. So it has applications in different fields like seismology, climate modeling, economics, environment, material research, drug design, manufacturing, and medicine and biology. And in many fields, it is having applications. So So, and mathematical models classification, first we'll understand what is the classification of the mathematical models. And there are, so we'll understand here three types basically. So, steady state versus dynamic models, and lumped parameter model versus distributed parameter models, and deterministic model versus stochastic models. So, steady state is nothing but steady state model is nothing but it is time invariant, that is the process parameter does not vary with the time, it is stationary. So an unsteady state or dynamic models are nothing but they are transient or dynamic, that is the parameters will change with time. And what is the difference between lumped parameter and distributed parameter model? So lumped parameter model is nothing but, so in that the spatial variations are ignored, that is the various properties and the state of the system can be considered as homogeneous throughout the entire volume. And so whereas distributed parameter model it takes into detailed variations into account and variations in behavior from point to point throughout the system. So therefore distributed parameter model gives the partial differential equations, whereas lumped parameter model will give ordinary differential equations and it easy to solve compared with the distributed parameter model. And deterministic versus stochastic models. So deterministic are rigid models described by differential equations, integral equations, and linear equations. Whereas the stochastic, or this is also known as probabilistic model, which represents the distribution of discrete and continuous variables and also the probability distributions. And now we'll understand what are the uses of mathematical models. And mathematical models are useful in all phases of chemical engineering, from starting from research and development to plant operations, and even in business and economic studies. So therefore, so in research or development, so the use of mathematical models is it is used to determine the kinetic mechanisms and parameters from laboratory or pilot plant reaction data, and also the exploring the effects of different operating conditions for optimization and control studies, also used in scale up calculations. And next, the design, the uses in designs include, that is you have exploring the sizing and arrangements of processing equipment for dynamic performance, and the studying the interactions between various parts of the process, and evaluating an alternative process and control strategies, and simulating startup and shutdown and emergency situations and procedures. And also it also used in the plant operations, like whenever you have troubleshooting control and processing problems. And it also helps in startup and operator training, and studying the effects and requirements for expansion of the projects, and optimizing the plant operations. So it is much cheaper and safer and faster to conduct the kind of studies using mathematical models than the experimental. So this is not to say that the plant tests are not needed, but however, you need to conduct the plant tests. But before conducting the plant experimental tests or pilot plant, you need to understand mathematically. So if it is feasible mathematically, then only we can go for the pilot plant or real commercial plant. And now you understand what are the principles of formulation. So how do you formulate the mathematical models? So what are the principles to understand or write the mathematical model? So there are five principles. Like first, what you should understand, what is the basis, and what are the assumptions used in the process, and what is the mathematical consistency of the model, and what is solution of the mathematical model equations, and verification. And basis is nothing but the mathematical models, the basis is nothing but the conservation of mass, energy, and momentum. And these include the, so that is the process should be written in the form of continuity equation or energy equation or momentum balance equation, depends on the process you consider. So, and assumptions, generally, whenever you write the mathematical models, the assumptions are very important. So, but assumptions are should be validly made. You should not assume whatever you like, because the relevant assumption should be made. Then only your model will be good. So, like if you assume isothermal system means if there is point to point variation of temperature is very less, then you can use isothermal system. So if temperature variation is more, so you cannot assume isothermal system. So therefore, the assumptions part is very important whenever you design or write the mathematical models. And mathematical consistency of the model. So consistency means mathematical, after you write the continuity or energy or momentum balance, you get set of equations. After you write set of equations, you need to find out whether that equations are consistent or not. So for that, you need to find out those equations include how many variables are there. You have to count how many variables are there, and you have to count how many equations you got, and then write down number of equations equal to n, and number of variables is equal to m. And the degrees of freedom you need to find out. What do you mean by the degrees of freedom is, the degrees of freedom is nothing but the number of variables free to choose to optimize the process. And degrees of freedom is called f is equal to m minus n. So if degrees of freedom is 0, then m is equal to n. So that is you have unique solution. You have only one solution. If m is number of variables are more than the number of equations, it is nothing but over specified, and there is a scope for optimization. And if m less than n, that is called under specified, and but it is called contradictory solution. You cannot solve that problem, is not well formulated, and you have to recheck the process and write the equations. If something is not well formulated, and you have to recheck the process and write the equations. If something is wrong with the formulation of the that is, if it is over specified or under specified, and checking to see that the units of all the terms in the equations must be consistent. And finally, the fourth one is solution of the model equations. After you identify the model, write the equations and check the consistency. Then, so you have to check for the solution. So that is what are the methods to available to solve the type of equations you got, whether they are ODEs or PDEs or algebraic equations. Depends on that. You need to choose the type of method and then solve it. And after you solve that, you have to verify, that is, whether the results obtained are showing the real world situation or they are matching with the existing data. Then you have to check if they are okay, so then the model is. So now we'll discuss different examples of mathematical models of chemical engineering systems. After you understand what do you mean by mathematical modeling and what is simulation and uses and applications of modeling and simulation, now we'll start with simple examples like the chemical engineering systems from different like chemical reaction engineering, heat transfer, and mass transfer, and different examples. We'll discuss how to model the problem you take from the different subjects. So now the five examples in this unit we'll discuss, like series of isothermal constant hold up CSTRs, that is continuously stir tank reactors, and continuously stir tank reactors with variable hold ups, and two heated tanks, gas phase pressurized CSTR, and non-isothermal CSTR. And one by one we'll discuss how to model. That is, we'll take a problem and then describe the problem and understand the physical process and write the relevant equations. And finally you have to check the degrees of freedom, that is consistency. And finally you have certain number of equations. So now first example, this is series of isothermal constant hold up CSTRs. So that is the problem now we are considering is the product B is produced and reactant A is consumed in each of three perfectly CSTRs, three perfectly mixed CSTRs, and by a first order reaction occurring in the liquid phase. And assume that the temperatures and hold up volumes of three tanks can be different, but both temperature and liquid volumes are assumed to be constant. So thereby now we are considering isothermal and constant hold up, and density is also assumed to be constant throughout the system, so which is a binary mixture of components A and B. And this is the representation of three CSTRs in series. And the three CSTRs, the F0 is the flow rate, volumetric flow rate into the first tank with initial concentration of Ca0. And inside the reactor you have volume V1 and rate constant K1, and F1 is the outlet of the tank 1, and Ca1 is the concentration of the outlet tank 1, and it is entering into the tank 2 with hold up volume V2 and K2, and outlet flow rate is F2 and concentration is Ca2, and outlet flow rate of the third tank is F3 and Ca3. So now if the volumes and density of each tank are constant, so generally volume and density constant means, that means the mass of the system is constant. So therefore now the total continuity of the first reactor. So you have to write for this system, 3CSTR in system, you have to write total continuity equation and component continuity equation you have to write. And energy equation is not needed because you have assumed isothermal system. So therefore, in order to write the total continuity equation of the system, total continuity equation is nothing but mass into the system, that is flow of mass into the system minus flow of mass out of the system is equal to time rate of change of mass inside the system. So in the first tank, it is entering the F naught flow rate and with Ca naught concentration, and the first tank, the contents of the mixture will have density of rho 0. So therefore, so you have F density into flow rate will give the mass. So that is F naught into rho. It is the mass entering into the first tank. Rho into F1 is the outlet of the mass of the first tank. That is equal to time rate of change of mass inside the system. D by dt of density into volume is the mass. But here the density and volume are assumed to be constant, so therefore mass is constant. That means right side it will be zero because there will not be changing the mass. So thereby you get F naught is equal to F1. So that is flow rate, inlet flow rate of the first tank is equal to outlet flow rate. This is happening because of the density and mass are constant. If you consider variable volume, so inside the derivative density will come out and you will have dV1 by dt. So similarly, the total mass balance on second and third tank and so on, if you write, you will get F naught is equal to F1, which is equal to F2, and is equal to F3, which is equal to F. So this is the total continuity equation of the three tanks in series. And then you have to write the component continuity equation, because it is the reaction is taking place, product B is forming from the reactant A as per the rate, that is first order dynamics. So therefore, so you need to write the component continuity equation. The units of the component continuity equation are, so that is moles per A, whereas the units of the total continuity equation are, that is mass per time. And this is the component continuity equation, that is flow of moles of jth component into the system and flow of moles of component out of the system, and plus time rate of formation of moles of jth component from the chemical reaction equal to time rate of change of moles of jth component inside the system. And for the first tank if you write, so that is component continuity equation. So it is component continuity equation is, so flow of moles you want to get means, that is, so from the component continuity equation we understood that the flow, all the flow rates are equal to, that is single flow rate F. So therefore you need not write F naught, F1 and F3, F2. So therefore F is the total flow rate. F into flow rate into concentration will give mole per time. F is meter cube per time and concentration is moles per liter or moles per meter cube. So then you will get moles per time. Each term you will have moles per time. That is F into Ca naught minus F Ca1 for the first tank, in minus out. Flow of moles of A in minus out, plus rate is minus Ra into volume. So that is minus Ra, he says it is first order dynamics, therefore minus Kca. So Ra is Kca power n. So therefore n is 1, therefore Kca power 1 you can write. Right side is equal to d by dt of change of moles within the system. That is volume into concentration will give the moles. So therefore, rate you can replace with minus K1 Ca1 into V1. So first equation is F common. So you will have the ODE, ordinary differential equation. Similarly, you can write the for the second tank, so that is F into Ca1 minus Ca2 minus K2 Ca2 into V2 and V2 dCa2 by dt. So and third tank you have F into Ca2 minus Ca3 minus K2 Ca3 into V3 is equal to V3 dCa3 by dt. And the specific rate constants you need to calculate, so using the Arrhenius equation, that is k is equal to kn. N is 1 2 3 3 reactors, so alpha e power minus e by rtn. So if the temperature is different, the k's are different. Okay, so therefore, so here the energy equation is not required because we have assumed isothermal operation. So the three first order linear ordinary differential equations we got 1 2 3 equations, whatever you got 1 2 3. So these are the model of the three CSTRs in series with constant hold up, and the parameters must be known are, so you have three equations and you have to count what are the variables known, what are the variables unknown, and find out degrees of freedom. So therefore, V1, V2, V3, K1, K2, K3 must be known. that is volume of tank 1, volume of tank 2, volume of tank 3. Rate constant K1, K2, K3 should be calculated from the Arrhenius equation, and these 6 parameters must be known. And the variable that must be specified before these equations can be solved are the flow rate must be specified, and the initial concentration also should be specified. The initial conditions of three concentrations, that is their values at the time t is equal to 0, also must be known. So that is Ca1 when time t is equal to 0, Ca2 when time t is equal to 0, Ca3 when time t is equal to 0 must be specified. And now you have to check for the degrees of freedom. So that is, now you understood what are the how many number of equations are equal to 3. 1 to 3 are number of equations. They connect with different variables like ca1, ca2 and ca3 are unknowns. So therefore number of equations equal to 3, number of variables is equal to 3, and degrees of freedom is nothing but number of variables minus number of equations, that is m minus n, and which is equal to 0, and you will have unique solution for these ordinary differential equations. And if you simplify the equation, dca1 by dt is equal to fca0 by v and fca1 by v minus vk1 ca1 by v. And here you can simplify this like tau is residence time is volume by volume one ca1 by v. And here you can simplify this like tau is residence time is volume by volumetric flow rate. You can write the equation in terms of the residence time also. So dca1 by dt is converted into residence time 1 by tau ca1 naught minus, so this is dca1 by dt plus k1 1 by t ca1 is equal to 1 by tau ca naught. So this is the first equation. Similarly second equation and third equation, and you need to solve these three equations using any mathematical tool. So therefore for this example, now you understood how to write the model equations. Finally the 3 CSTR in series system is represented by these three ordinary differential equations. You need to solve them, that means you need to find out a mathematical tool to solve these three equations, that is simulation. So you can solve these three by means of writing a simple C code, or you can use MATLAB, that is, so you can ODE solver you can use to solve these three differential equations. And similarly you can understand next problem will be like CSTRs with variable holdups. So the difference between the previous one CSTRs with constant holdup and this is variable holdup. So in the just now whatever 3 CSTR constant holdup CSTR series is, we have assumed that holdup volume, that is v1 v2 v3 is equal to v, it is constant. Whereas if you assume thereby you got right side is 0, all flow rates are equal to single flow rate. So now if you assume hold up is variable, that is if it is changing, then you cannot assume volume constant. And also here you assume, earlier you have assumed first order, if you assume nth order, then the equations for the same problem, the equations will be different. That is, you have to write total continuity equation and component continuity equation for tank reactor 1, reactor 2 and reactor 3. Total continuity equation is same continuity equation. The difference is the d by dt right side whatever you are seeing. So v1 into rho, earlier we have taken because volume and density are constant, so right side was 0, so therefore f naught is equal to f1. Now we are assuming that volume is not constant, variable volume, therefore it will remain in the derivative, and you have a equation here, that is dv1 by dt is equal to f naught minus f1. So similarly component continuity equation also, here it is the difference is earlier problem it is first order, therefore minus k ca power 1 we have written, here k ca power n you have to write. So then continuity equation another equation, total continuity equation one equation. So similarly for reactor 2, so similarly you write the component continuity equation, that is you get f1 minus f2 is equal to dv2 by dt, and the component continuity equation is f1 ca1 minus f2 ca2, and V2 K2 Ca2 power n is equal to dy dt of V2 Ca2. Similarly, for reactor 3, dV3 by dt is F2 minus F3 and component continuity equation we have. So now here the earlier problem you got three equations because continuity equations, the mass density, volume and density are constant. Therefore, you don't have three differential equations for total continuity equation. Whereas here variable volume, so instead of three you got six equations, three equations for continuity equation and three equations for component continuity equation. Now you can solve the six equations, six first order nonlinear equations. The parameter must be known are again K1, K2, K3 and N is the what is the order of the system. And initial conditions for all these dependent variables are to be given, that is CA1, CA2, CA3, V1, V2, V3 at initial conditions time t is equal to 0. And the forcing functions like ca naught and f naught must also be given. And now you have, in order to check the degrees of freedom, you have number of equations are 6 and number of variables are 9, like ca1, ca2, ca3, v1, v2, v3, f1, f2, f3, 6 variables. So clearly the system is not sufficiently specified and solution will not be obtained because variables are 6 and equations are, variables are 9, equations are 6. So now you recheck the things and see where you went wrong. So therefore, generally the common configuration whenever you have these three CSTR in series, you have a flow rate that is it depends on the volume of the tank. You need to control the flow. So F1 is a function of V1, F2 is a function of V2, F3 is a function of V3. So these three equations also called controller equations. Now you have number of equations will be earlier 6, now 3 plus 9, number of variables also 9, therefore degrees of freedom is 0. So now you can solve the system and this is said to be consistent.